Hi physicists. So this is the question we did on the board today. As I said, I wanted to do it again so you could see a little bit more clearly what's going on exactly, now that you've got a little bit more of an understanding of what's happening. So, like I said, this is a pretty good question. So yeah, I'd just suggest you look over this if you're having difficulty with what's going on. Alright, so as I said, this is exactly the same one we did today, so if you understood it today, turn off now, there's no need for you to see it again. Okay, so for our I guess the main parts of this question we need to take into account. Up the top here, we have our work function, 2.3 electron volts, and we know that we have a stopping voltage of 4.5 volts. So when our voltage is 4.5, that's enough to overcome the kinetic energy of the electrons so they can't reach the cathode. Okay, so remember, there's our two sides. Okay, our electrons are here, they get a kinetic energy, they move in that direction, but this is negatively charged, and at 4.5 volts, there is enough potential difference that the negative charge, the repulsion here, overcomes the kinetic energy of the electrons. Okay, so the way to think about this, the electrons have a certain amount of kinetic energy. They have to lose all of that energy in order to be pushed back. Okay, so I guess what we need to think about here is work done. So remember, work is just a change of format of energy. So our work is QV. Okay, now, excuse me. So the way you need to think about this, so our electrons start with a certain amount of kinetic energy. They need to lose that kinetic energy if they are not going to make it all the way across. Okay, so the easiest way to do this, if you're not quite understanding that concept, is just to remember this that I showed you today. So, whoops, EK max is equal to V0. So V0 is our stopping voltage, and our maximum kinetic energy, that's our maximum kinetic energy of our electrons. So remember, our electrons have different amounts of kinetic energy depending on how much energy they needed to use to get out of the metal atom. But for the ones that are on the very outside, the ones that are least tightly bonded, they're the ones that will have maximum kinetic energy. So in this case, our kinetic energy maximum, which is equal to our stopping voltage. So our stopping voltage is 4.5 volts, so therefore our kinetic energy maximum must be 4.5 electron volts. Okay, so our maximum kinetic energy is EK max is 4.5 EV. Okay, now we can put that into joules as well if we like. So remember, to get EV into joules, we just multiply by 1.6 times 10 to the negative 19. My handwriting's going a bit weird there, sorry about that. Okay, so let's try this. 4.5 times 1.6 times 10 to the power of negative 19. And we get, there we are, 7.2 times 10 to the negative 19. Oops, 2 times 10 to the negative 19. Okay, so there's our first, whoops, it's in joules. Okay, so for the second part, so first of all, our electrons leave with that much kinetic energy, and that's how much they lose getting across the gap. So they lose all of that kinetic energy, so they never make it across. Okay, and that's how we can, evaluate our stopping voltage compared to our kinetic energy. Now we want the electron speed at this kinetic energy. Now, like I said, this shouldn't be too much trouble for you guys. I might try and zoom in a little bit. My handwriting's bad. So remember, our kinetic energy is equal to 1/2 mv squared. Okay, so if we rearrange this equation, we get 2ek on m. Square root of that will give us v. Okay. Now we just plug in our values. So we want. So V is going to be equal to 2 times our kinetic energy. Now remember, if we're using, the kinetic energy equation, this needs to be in joules. So 2 times 10 to the negative 19 over the mass of an electron which is 9.1 times 10 to the negative 31. Square root of that whole thing will give us our maximum, or our speed at that kinetic energy. So again, let's work this out. 2 times 7.2 times 10 to the power of negative 19. Now, I like to work these out in bits. I know not everyone does, but I don't know, I just do. I prefer it. Okay, so there's the first bit. That's the top of our equation. You could do this with brackets, I guess, but I don't know. I just like it this way a bit better. Divided by 9.1 times 10 to the power of negative 31. Okay. And then we need the square root of that whole thing. Oops, not like that. Square root of this whole guy over here. Okay, so there is our kinetic energy. So, that's our velocity. So our velocity is equal to 1.26 times 10 to the power of 6 meters per second. Okay, so the wavelength of the radiation that is incident on the sodium surface. Okay, so for this we need to think a little bit more carefully. So we need to remember that this formula, our EK max, is equal to Planck's constant multiplied by the frequency minus the work function. Okay, so that's just an equation I'd expect you to remember. So if we again rearrange this now, we need wavelength. We can't get wavelength straight up, okay? But we can get frequency, and anytime you can get frequency, you can get wavelength. So let's rearrange, and we get EK. I'm just going to shorten it to EK for the moment. Plus, phi over H will give us F. Now, if EK is in electron volts, which is the easiest way to do this, we need H in electron volts as well. Now, the easiest way to do this, because our work function is already in electron volts up at the top of our equation. Okay, so our work function is 2.3. We know our kinetic energy is 4.5. So this becomes a pretty straightforward equation. F equals 4.5 plus 2.3 over, and remember H is 4.14 times 10 to the negative 15. Okay, so let's have a look at this. So 4.5 and 2.3, that is 6.8, divided by 4.14 times 10 to the power of negative 15. Okay, so there's our frequency, 1.64 times 10 to the power of negative 15. To the 15, not to the negative 15. 1.64 times 10 to the 15. Hasn't asked for frequency though. Okay, it's asked for wavelength. So you need to remember this. C equals wavelength times frequency. Never forget this. Okay, you will often need to convert between wavelength and frequency, and that is how you do it. So we have our frequency. We know what C is, so let's rearrange this, and we get that. So our wavelength is 3 times 10 to the power of 8 divided by 1.64 times 10 to the 15. So 3 times 10 to the power of 8. Okay. Divided by this one. Okay, and we get 1.83 times 10 to the negative 7. But again, remember, we usually do wavelength in nanometers. So to convert this to 10 to the negative 9, that's 183 nanometers. Okay, so 183 nanometers. Or 1.83 times... Oh, sorry, that's not a 3, that's a 7. 1.83 times 10 to the negative 7 meters. Same thing. Okay. So we have the wavelength of the radiation that's on there. Now we need the minimum frequency of light that will cause the emission. Now our minimum frequency is our threshold frequency. Okay, and so remember, our work function is the minimum energy to remove an electron. This is actually the easiest part of this question now that I think about it. And our work function is equal to H F naught. Okay, F naught is our threshold frequency, H is Planck's constant, and phi is our is our work function. Okay, so again, we rearrange. F naught equals phi on h. Now remember, phi is 2.3. And again, if we've got that in electron volts, we need h in electron volts as well. You just leave it like this. It's just much easier doing it this way. You could convert to joules, but geez, I don't know. Why would you? It's just much easier if you're given the work function as it is in electron volts. Let's just use electron volts. Okay, 2.3 divided by Planck's constant in electron volts, which is that. And we get, oops, sorry, that's something else I'm doing at the same time. Okay, where are we? 5.56 times 10 to the negative 14. (10 to the negative 14). Oh, hang on, not negative 14. What am I doing? Positive 14. Thought that was a very small frequency. 10 to the 14 hertz. Okay, so as I said, this is a pretty typical example of an exam question. It's good because it uses a lot of the equations we've seen so far, and you need to know, what everything means. You need to know that, work function is equivalent to, over here, work function is equivalent to Planck's constant multiplied by the threshold frequency. So you need to know what the work function is and what the threshold frequency are. So just be aware of those two terms and your stopping voltage as well. Remember, your kinetic energy, your maximum kinetic energy is only equal to your stopping voltage if your kinetic energy is in electron volts. Okay, so as long as your stopping voltage is in electron volts, that'll be the same as your, as long as your electron volt, let me start again. As long as you have a voltage, your kinetic energy is that same voltage in electron volts. Okay, so if you've got a 4.5 volt stopping voltage, so your kinetic energy maximum would be 4.5 electron volts. All right, I hope this has made a little more sense. If there's any part of this that you're not quite understanding, that you're not quite getting, please come and let me know. This is super important for your exam. You need to know about the photoelectric effect, how it works, and how to calculate things from it. So yeah, please let me know if you have any problems. See you guys.